So I was saying that from the second law of thermodynamics, we saw how entropy can be used to determine whether a reaction is spontaneous or not. Yeah. So we saw that for spontaneous reaction, the total entropy or the entropy of the universe, which now this includes the system and the surroundings, is greater than zero. Then there you say that you have a spontaneous reaction. And if the maximum entropy, if it is equal to zero, then you talk about an equilibrium process. Now, if you have a system which is in contact with the reservoir at a temperature T, in which you have an infinitesimal irreversible process occurring, and the only work done being the pressure volume work. Now, the pressure volume work here, we're talking about where you consider a system where you have a cylinder that is fitted with a piston. So any work that the system is doing is moving this. So there's a changes in volume and the changes in pressure, which results now in movement of this piston. So we had a consideration where we said for such a system, work is given by minus P dV. So if you have a system that is in contact with a reservoir at temperature T, and then you have it's an infinitesimal irreversible process, which has only this pressure work volume. I'd like to take you back a bit to just a recap that we covered at some point about irreversible work. So here, when we're talking about irreversible works, we said that this integral for an irreversible cycle is always less than zero. And the entropy of the final state is always greater than the entropy of the initial state. Okay. So for an irreversible process, we had this, say this dq over t is always less than zero. So as most processes going on in nature are spontaneous and irreversible, there is this statement that applies that the entropy of the universe always tends towards a maximum. So the entropy of the final state for an irreversible spontaneous process is greater than the entropy of the initial state. So having that in mind, we can go back to where we are today. Saying for this system, if Q is the quantity of heat exchanged with the reservoir, then since the process is irreversible, the entropy ds for the system is greater than Q over T. So this expression applies for such a system. ds is greater than Q over T. Now, if you rearrange this, then TdS is greater than Q for this process. So the entropy of a system remains unchanged in a reversible change. So remember, for a reversible change, we said, so entropy is a state function. But since for a reversible change you are moving, you can move in a cycle, then you say that the entropy remains unchanged, okay, for such a system. But for an irreversible system, as we have seen, the entropy increases. So we have these expressions for entropy. So the sum of all changes in entropy equals to 0 for a reversible change. And the sum of all changes in entropy is greater than 0 for an irreversible change. So these are, we saw this from the second law of thermodynamics. We saw that you can have the sum of the change in entropy for the system and the change in entropy for the surroundings being equals to 0 for an equilibrium process, and the sum can also be greater than 0 for a spontaneous process. So combining these two expressions, you can say that the sum of these two can either be greater than or equal to 0. And just a second. I think there's a repetition here. So you're saying that when you combine the two relations, this can either be greater than or equals to 0. Now, since, remember the expression we had, that TdS is greater than Q. So we had this expression, yeah? We said that TdS is greater than Q, the expression that we came up with in E1. So let me just go back. So now, if this is the case, then this expression is the same as 0 is greater than Q minus TdS, okay? So of course, from this expression, this is the same as this one here. That is Q minus TdS is less than 0. So then we can say that Q minus TdS is a negative. Is negative because it's less than 0. Okay. Now, since you're only concerned about the work that is done in this system, is the pressure volume work, then you know this expression here. This expression comes from the first law, that is du equals to Q plus W. Okay, but we said that W equals to minus P dV. So therefore, du equals to Q minus P dV. So from this, we can say that Q equals to du plus P dV. Okay. Now, if we now put this into our expression, E2, which said Q minus T ds is less than 0. So if you put the value for Q now from this expression here, you get du plus P dV minus TdS is less than 0. So this is an important expression from which you're going to arrive at a couple of properties for the system. So just hold on that for a second. So this inequality that we have ended up with here is applicable if a spontaneous change occurs and the only work involved is the pressure volume work, as you have stated at the beginning. So now, if volume and entropy of the system are held constant, so here talking about V, here talking about S. If they are held constant, then that equation is going to change. So let's just look at it. If V and S are constant, what happens here? It means that dV is going to be equals to 0, okay? And ds is also going to be equals to 0. So therefore, you end up with this expression, du at constant volume and entropy is less than 0. So remember here we are coming from this expression, du equals du plus P dV minus TdS being less than 0. So at constant volume and entropy, these two terms are eliminated. So you remain with only du being less than 0. So therefore, here you can say that for any irreversible process in a system of constant volume that does not change in entropy, the internal energy decreases. So when you say that du is less than 0, here essentially it means it's negative, yeah? So for a negative change, it means the final state is lower than the initial state, okay? So in other words, for a conservative mechanical system, the stable state is the one with the lowest energy. So that is the meaning, the physical meaning for this inequality that we have come up with here. So for a conservative mechanical system here, essentially we're talking about the volume is not changing and the entropy is not changing. So therefore we're saying for this system, the stable state is where the lowest energy is one with the lowest energy. So the role of the internal energy on position of equilibrium is that in systems of constant entropy, the equilibrium position is in the direction of lowest energy. So for this system where you don't have, where you have its constant volume and the entropy is the same, the system is going to move towards the lowest energy possible for that particular system for it to attain equilibrium. So that is the tendency for this particular system. Now, you can also consider where volume and internal energy are held constant. So remember, our expression is this, du plus p dv minus TdS is less than 0. So where volume and internal energy are constant, so now this system has been isolated. So what happens is that this du's, when the internal energy is constant, this one is also equal to 0. And dV with volume constant, this one equals to 0. So we remain with this expression, minus TdS at constant internal energy and volume is less than 0. Now, when you multiply this by -1, both sides, and then divide by T, so when you, of course, when you divide by negative, you also change this inequality here, okay? So it becomes now, when you multiply by negative, it becomes TdS is greater than 0, of course, and then divide by T, both sides. You end up with the expression that is ds at constant u and v. So ds is greater than 0. So the meaning of this inequality is that the entropy must increase in such an irreversible process. And this implies that in systems of constant energy and volume, such as isolated systems, so you don't have any exchange of energy between the system and the surroundings, and the volume is also constant, the equilibrium position for this system is in the direction with the highest entropy, because we get that from this expression here. That is ds at constant u and v is greater than 0. So it's always it's increasing. The system would move towards higher entropy. Now, for the system which is not isolated, there are entropy changes in the adjacent systems, which must also be considered, okay? So for a system where you have the volume is constant, so it's an irreversible process. The volume is constant, but because it's not isolated anymore, then any changes in entropy on adjacent systems would have implications on the entropy of this system. So that means ds du is not equals to 0, like it was in this case for this expression here. So in this case, what happens, since the volume is constant, this term PdV becomes 0. So you remain with du minus TdS being less than 0. So du minus TdS at constant volume is less than 0. Now this expression can also be written as change or d into brackets u minus ts at constant volume is less than 0. Okay. Now this quantity here, u minus ts, is referred to as the Helmholtz free energy, and it is represented by the letter A. So we can say that A equals to u minus ts. Okay. Now when you differentiate this equation at constant temperature, so what happens here? dA equals to du minus T ds minus S dt. But since we are talking about constant temperature here, then this term is going to be equals to 0. So essentially dA equals to du minus TdS. So as for a spontaneous process, equation E6 is this equation here. That is du minus TdS at constant V is less than 0. So here we have said that dA equals to du minus TdS. So this equation E6, essentially this here is the term A. This is, can say this is dA, okay? So this expression becomes dA at constant temperature and volume is less than 0. So in other words, what we are saying from this expression is that in an irreversible process at constant temperature and volume, the Helmholtz free energy decreases. Just a second. So they're saying that for an irreversible process at constant temperature and volume, the Helmholtz free energy A decreases. That's the meaning of this expression. So for a system at constant temperature and volume, the PV work term will be 0. Okay. So the system does no work for this system, which is at constant temperature and volume. So the system, since the system does no work, we can say that dA equals to 0. Therefore, the condition for equilibrium for a system that cannot do work is dA equals to 0. Okay. So most physical processes and chemical reactions of interest are usually carried out in the laboratory at constant temperature and pressure. Now, for such processes, the equation E3 can be written as this. So remember, E3 was du plus PdV minus TdS is less than 0. Okay. So this expression we can simplify it to become as this, to indicate constant temperature and pressure. Now this quantity here, U plus PV minus TS, is referred to as the Gibbs free energy and is represented by the symbol G. Now in G essentially equals to U plus PV minus TS. But U plus PV is enthalpy. So essentially G equals to H minus TS. Now for infinitesimal change and isothermal conditions, that is dt equals to 0. So here, this is the same dg, that is for infinitesimal change. Dg equals to dh minus tds minus s dt. But then we are saying under isothermal conditions, dt equals to 0. So therefore, this term here becomes equals to 0. So dg for under isothermal conditions is going to be equals to dh minus tds. Now, this is an important relationship, and it means that for a change at constant temperature, where only mechanical work is done. So mechanical work, you're talking about the PV, pressure volume work. The free energy is equal to the enthalpy change minus the product of the absolute temperature and the entropy change. So equation E3, E3A that is, so remember E3A is this one here. This represents G, yeah? E3 becomes dG at constant temperature and pressure is less than 0. So this is thus in an irreversible process at constant temperature and pressure, in which only pressure volume work is done, the Gibbs free energy decreases. So since both G and A, G, that is the Gibbs free energy, and the Helmholtz free energy, are defined by an explicit equation in terms of variables which depend on the state of a system. Both of these are thermodynamic properties, that is A, G, and A. And the differentials are complete differentials. So mathematically, for a cyclic process, we are saying that these are thermodynamic properties. And because they are defined by variables that are state functions, they are also state functions as well. So for a reversible cycle, a reversible cyclic process, the differential dg equals to 0, because you're talking about a cyclic process. The same for the differential for dA is also going to be equals to 0. Now, when you consider an irreversible process and a reversible process, which involve pressure volume work, these expressions are true. That is ds for an irreversible process, ds at constant u and v is greater than 0. Du at constant v and s is less than 0. dA at constant t and v is less than 0. dg at constant t and p is less than 0. Now, for a reversible process, all these are equals to 0. That is ds at constant u and v equals to 0. du at constant v and s equals to 0. dA at constant t and v equals to 0, and dg at constant t and p equals to 0. Now, these relations may be applied for finite changes as well as for infinitesimal changes. So for finite changes, you're going to use delta in the place of d. So this, for example, this one will become delta S for a finite change at constant u and v is greater than 0. Okay. So spontaneous changes always go to the minimum. Okay. Spontaneous changes, you're talking about these ones in an irreversible process. That is, as in the Gibbs free energy at constant temperature and pressure. We said the Gibbs free energy will always tend towards the minimum, and they tend to the maximum, as in the case of entropy of an isolated system. They don't move to some other conditions, even though the change to some other condition satisfies the required inequality. So always, for spontaneous changes, go to the minimum in the case of dg, or these other properties. They would tend towards the minimum, and entropy would tend towards the maximum. Okay. They would not be in between. It's either minimum or maximum. So as much as, although in between might satisfy the inequality, for example, ds being greater than 0, in between, of course, it would be greater than 0, but still, it is only satisfied when that is, the entropy has moved to the maximum. So in these definitions, or in these derivations, we have restricted ourselves to systems which involve pressure, volume, work. But if you have electrical work being done by the system, or if temperature changes, the criteria for equilibrium will be altered. If a system is at constant temperature and pressure and does no additional work, the condition for equilibrium is dg equals to 0. So G will be at minimum when the system is at equilibrium, as can be seen in this figure. So this is a system where no work is being done, and it is at constant temperature and volume. We're talking about this one here for a reversible process. So here,
Kigolo kamati iwi.
I always find it interesting how you guys are attending classes. So you're walking and your camera is on, I don't know, just listening. I thought you would be taking notes. Otherwise, it's so difficult to follow if you're just watching the presentation. But if you're watching and then taking notes as well, it makes sense when you're going through the slides later. Anyway, so we're saying that for this expression here, the system is at constant temperature and volume, temperature and pressure, and does no additional work. The condition of equilibrium is dg equals to 0. So here G I'm going to be kicking people out from the class. Continue interrupting me every time. So this figure here, this is what this figure is illustrating, that at position of equilibrium, G will be minimum when the system is at equilibrium. So that is at this position here. We have minimum G. This curve here represents the variation in the Gibbs free energy as the system moves towards equilibrium. So at this point, we have minimum G value. And this is the position of equilibrium for a system that is at constant temperature and pressure. Now let's talk about free energy and boiling points. What are the implications of free energy and boiling point, or on boiling points? So the question is, does water at 1 atmosphere pressure boil at 373 Kelvin? Okay, this is 100 degrees Celsius. Now, when water boils, the process is a reversible process, because of course it can condense back to liquid. So it does not just vaporize irreversibly, but it's a reversible process. So the slightest fall in temperature or increase in pressure will cause condensation. Okay. For a reversible process, delta G equals to 0. That is, the conversion of water to steam or steam to water does not change the total free energy of 1 mole of water at 1 atmosphere and 373 Kelvin. So we can write this expression, delta G equals to delta H minus T delta S, which equals to 0 at the boiling point of water. Now, when you consider another change here, this is still the boiling. Yeah? For this change, you're moving from liquid to gas. Delta H, there is a fixed delta H and there's a fixed delta S from this expression here, because it needs to satisfy this expression at the boiling point. So that means it has a fixed value for the delta H and a fixed value for delta S. Now, any changes in the temperature will mean there's a change in the delta G value. Okay. So from this, it follows that there is a specific unique temperature T at which the boiling will occur. So below this temperature, below that particular temperature, so that means you have a smaller T now, then delta H is going to be greater than T delta S. Okay. And if we were to boil, if water were to boil, it would mean that a change for which delta G is greater than 0. So remember delta G from that expression there, delta G equals to delta H minus T delta S. So if delta H is greater than T delta S, then delta G is going to be greater than 0. So this means if delta G is greater than 0, this means that boiling is impossible below this temperature. Yeah, that is the temperature T, because here now delta G is greater than 0. Now, if you consider a case that is at a temperature that is above 373 Kelvin, in this case, now you have a higher value for T. So what that means is that now delta H is going to be less than T delta S. So what that means, if you have a greater T, then you have a greater T delta S. delta H minus T delta S is going to be less than 0, which means it means that for boiling now, delta G is less than 0. So let's consider this process here. I want to change something here because I don't like how they are written here. So this is T delta S. This is delta H. And this is delta G being equals to delta H minus T delta S. Okay. So here, considering another process, not boiling, but the melting of a solid. So here, the heat of fusion, that is the delta H fusion, is independent of temperature. So this is delta G against temperature. So since delta H is independent of temperature, it's going to be a horizontal line. It does not change with temperature. It is constant. But now, as you change the temperature, T delta S is going to be changing. Okay. So here, as you're moving in that direction, T delta S is increasing. Okay. And then what happens? As T delta S is increasing, delta G, which is given by delta H minus T delta S, is decreasing. So this is this line here. Okay. So at a certain point here, these two lines, that line for T delta S and for delta H, they meet. Okay. So that means delta H and T delta S are the same at this particular point. So what that means is that this expression delta G becomes equals to 0 at that point. So that means at this point, melting would take place. But in any other direction, for example, in this direction, fusion is impossible. But beyond, so notice here, beyond this, so let me just say this. Beyond this, you have cases where you have, okay, beyond this point, we have T delta S being greater than delta H. So that means delta G is less than 0 beyond this point. Okay. So therefore, beyond this point, fusion is possible, but below this point, fusion is impossible. Here you're talking about cases where delta G is greater than 0. So beyond, at points where delta G is greater than 0, fusion is impossible. At points where delta G is less than 0, then fusion is possible. There's melting of the liquid. So the figure shows the thermodynamic treatment change of state.
Excuse me, sir.
Yes.
Can you please go back to the graph? I have a question for you. What happens when T delta S? What happens to delta G when T delta S increases?
When T delta S increases.
Yes.
So remember this expression here for delta G. Okay. So when T delta S increases, delta H, remember, is constant. Huh? So that means when this increases, then it becomes less than 0. You understand?
Yes, sir.
So that is what happens to delta G as
Okay,
T
it is
delta S
okay.
increases. Yes.
So meaning that
let's take,
fusion will take place.
yes. No? What did I say? Yes, fusion will take place. Fusion is possible beyond this point. But below this point, fusion is impossible. Let's take 5 minutes and then come back. So again, just a recap of what we have discussed, that diagram, saying that the figure shows thermodynamic treatment change of the change of state. This time we're talking about the melting of a solid. Now the horizontal line shows that enthalpy change for the fusion, and this is taken to be independent of the temperature. Okay. Now the value T delta S, on the other hand, increases with temperature. And we understand, because as you increase the temperature, then the product of these two is going to be increasing as well. So at point A, T delta S equals to delta H. That is the point where the two lines met. And this is the normal melting point. So this is at this point here, where the two lines meet. At point B, delta H is greater than T delta S. And the melting is impossible because the change would give a positive delta G, or that is a delta G that is greater than 0. Okay. At C, melting can occur, and the process here is irreversible because we have delta G being less than 0. Okay, or we have a negative delta G. Now let's look at the properties of the Helmholtz free energy. Just a second. So we said the Helmholtz free energy is given by this expression here. That is A equals to U minus TS. Now, to understand the physical significance of this Helmholtz free energy, consider the change in A when the system passes from a state state 1 to a state 2. Okay. So of course, when this is changing, then you have changes in the variables in this expression. So this becomes, we can talk of delta A being given by A2 minus A1. That is the final value minus the initial value. Now this is going to be equals to U2 minus T2 S2 minus U1 minus T1 S1. Okay, so you understand here you're moving from, this is the final state, and this is the initial state. So now, this one you can open the brackets. Essentially here you see you have U2 minus U1. If you open the brackets, so U2 minus U1 is the same as delta U. And then into brackets T2 S2 minus T1 S1. Now, under isothermal conditions, T2 equals to T1 equals to the temperature T now, the isothermal, the constant temperature T. So if that is the case, this here becomes T, yeah? So that means you can take it out. So it becomes T into brackets S2 minus S1. S2 minus S1 is the same as delta S. So the expression here is delta A is the same as delta U minus T delta S. So by definition, we know that delta S is given by QR over T. Okay. Now, if this is the case, then QR is going to be given by TDS. So we can have in our expression here, we can substitute for the value of delta S, T delta S, I mean. So it's this, the expression becomes delta A is the same as equals to delta U minus QR, which is given by this expression here. Now, since from the first law of thermodynamics, for a reversible isothermal process, this is the first law, yeah? That is delta U equals to Q plus W. So that means delta U minus QR is the same as W. So here, this expression here, this part of the expression is the same as W. So here we are saying that delta A equals to WM. So therefore, at constant temperature, that is isothermal conditions, the maximum work, that is WM, obtained from a system is at the expense of increase in the Helmholtz free energy. So there's a change in the notes. This one makes more sense when you say increase because you're talking about a positive change. Okay. Now this is why A sometimes is called the work function, because delta A equals to WM and or the maximum work content of a system. So A sometimes is also referred to as the work function or the maximum work content of a system. Now, if we differentiate the expression for A, that is A equals to U minus TS. So what happens here? We get delta A equals to delta U minus TDS minus SDT. Okay. But TDS equals to QR. Okay. And QR is given by du plus PdV. Of course, this one we are getting this from the first law. So this means you can substitute this into our previous expression E20. That is du plus PdV. So this becomes dA becomes equals to du minus SDT minus du minus p dv. Hope you can see how we have arrived at that. So here, of course, du and du cancel out. So you remain with dA being equals to minus s dt minus p dv. Now at constant volume, that is dv is going to be equals to 0. So this means this one is 0. So what you end up with here, you have dA being equals to minus s dt. When you rearrange this, dA over dt. So remember, this was at constant volume. Eh? So this equals to minus s. This is the expression we have here. Now, at constant temperature, that is dt equals to 0. So what happens here? This one now, in this case, is equals to 0 now. So you end up with dA equals to minus p dv. You rearrange it, that is dA over dv, but remember this was at constant temperature, equals to minus p. This is the expression that we have here. So another equation which shows the variation of A and T can be given below. You have a quantity that is A over T. Differentiating it with respect to T at constant V. Just a second. So here, we're talking about A over T. So we want to differentiate this with respect to T. This one is the same as A to power T to power minus 1. So starting from there now, you can see how the different, how differentiating that expression, you end up with this expression here. So differentiating this with respect to T now, since you have two variables there, first of all, this with respect to, so first of all, differentiating this one first and keeping this constant, you end up with negative A T to power minus 2 plus T to power minus 1. Now you have kept that constant, and you differentiate A now with respect to T. Okay. So this expression here is the same as delta A over delta T of course at constant V, divide by T, that is from this part, minus A over T squared. Now, if you from here now, you can end up with this expression. That is, if you make T squared the common denominator. Of course, this is the same as this divided by this is T multiplied by delta A over delta T at constant V minus this divided by this is 1, so minus A. So you end up with this expression here. So this expression, remember this, we have the expression delta A over delta T at constant V. We have come across here in E22. It's the same as minus S. So that means if we change this, put minus S into this becomes minus ST minus A over T squared. Okay, so this is the same as, if you take the negative outside, it's the same as A plus TS. So minus A plus TS over T squared. But now, from the expression of the Helmholtz free energy, A plus TS equals to U. So therefore, this one, the expression, finally, we can say the differentiation of this A over T with respect to T at constant V equals to minus U over T squared. Okay. Let's look at isothermal change in the work function. So for isothermal change, dt equals to 0. So remember E21 was dA equals to no, just a second. That's something wrong. This one was minus S dt minus P dV. So now if you're talking about isothermal conditions, of course, this becomes 0. So therefore, dA equals to minus P dV. So for 1 mole of a perfect gas, P can be written as RT over V. So here, this is for a perfect gas, you're talking about an ideal gas. So the ideal gas law applies. So here, when you replace for P with RT over V, becomes dA equals to minus RT dV over V. So for an appreciable process, the increase in delta A, the increase delta A in the work function can be obtained by integration of the previous expression, this one here, between the limits of the initial state 1 and final state 2. So you differentiate dA within the limits A1 to A2, then differentiate, excuse me, the other part of the expression within the limits V1 to V2. So of course, this RT are constants. So this becomes A2 minus A1 equals to minus RT, the ln. So essentially this one, of course, the differentiation of the integration of this, you get the ln of V. But then you're talking about limits V1 and V2. So essentially you're talking about ln of V2 minus the ln of V1, which essentially can be written as ln of V2 over V1. So here, A2 minus A1 equals to minus negative RT ln of V2 over V1. But then if you remove the negative sign, it changes this to become V1 over V2. So delta A can be written as RT, the ln of V1 over V2. Okay, so let's look at the Gibbs free energy. So this function is defined by this expression here. G equals to U minus TS plus PV. Of course, this one we said can be written as, since H equals to U plus PV, this can be written as G equals to H minus TS. Since A equals to U minus TS, this expression can also be written, this expression here. So U minus TS is also equals to A. So the G can be written as equals to A plus PV. So for a process taking place at constant pressure, the change in free energy is given by this expression, delta G equals to delta A plus P delta V. Okay. If in addition, the temperature is constant. So at constant temperature, delta A is given by Wm. So therefore, this equation can change now under constant temperature. So additionally, if you have constant temperature, then delta G is going to be given by Wm plus P delta V. So the quantity Wm here, as we have mentioned, represents the maximum work that is obtainable in the given change. And it includes all types of work, such as electrical and surface work, in addition to the work expansion. That is the PV work. So the latter, that is work expansion, is equal to P delta V. And so W plus, just a moment. This one here, so W plus P delta V, just a second. This represents reversible work that is inclusive of work expansion. So you have, this one can be obtained in from a given change in state. My notes end there for today. Next you're going to get into the further describe these isothermal changes in free energy function. Then we look at a few examples, and then we look at now a combination of these two, the Gibbs free energy and the Helmholtz free energy, to come up with the what we call the